Hello everyone, my name is Nidhi Chauhan. I'm assistant professor in Gyan School of Pharmacy. That is a part of your Suresh University. And today we are going to discuss this topic, that is your polynuclear hydrocarbons. It comes in your pharmaceutical organic chemistry second, that is in your third semester, second year. So here we have already discussed few topics in this polynuclear hydrocarbon chapter, and in this unit also. And in this unit, we have already discussed that what is your polynuclear hydrocarbon, what are the types of what are the mainly polynuclear hydrocarbons that are mentioned in your syllabus, and we have also discussed about the reactions and the method of preparations of some of the polynuclear hydrocarbons, and they are also known as polycyclic hydrocarbons and polyaromatic hydrocarbons or polynuclear aromatic hydrocarbons also. And the naphthalene, we have discussed about the naphthalene and phenanthrene. So it's a method of preparations. What are naphthalene? What is its method of preparation? What is structure? And what is its method of reaction? Chemical reactions. We have already studied that, and in the phenanthrene also. What is the structure of phenanthrene? What is its structure, and what are the method of preparations and the chemical reactions, that also we have studied. So today we are going to discuss. So today's learning objective is that we are going to study about the polynuclear hydrocarbons, and also in the previous lecture I have told you about the method of preparation of the anthracene. Today we are going to study about the chemical reaction of the anthracene and its uses, and the fourth compound of this polynuclear hydrocarbon is your dimethylmethane, and its method of preparation and its uses and its chemical reactions. And also we are going to study this trimethylmethane and its method of preparation and its uses. And the student outcome is that they were going to know about polynuclear hydrocarbon. Also, they are going to know about the anthracene and the uses, and they are also going to know about the dimethylmethane and also the trimethylmethane and its method of preparation, their chemical reaction, and its uses also. So these are the things that we are going to discuss in this lecture, today's lecture, and then after that there is a completion of this polynuclear hydrocarbon unit. After that, we are going to start the fifth unit, that is the last unit, cycloalkanes. So let's start. So in this polynuclear hydrocarbons, the polynuclear hydrocarbons is a hydrocarbon made up of fused aromatic ring molecule. These rings shares one or more sides and contain delocalized electrons. Another way to consider PAH is molecule made by fusing two or more benzene ring. Polynuclear aromatic hydrocarbon molecule contain only carbon and hydrogen atoms. So these polynuclear hydrocarbons, or you can say polynuclear aromatic hydrocarbon, polycyclic and hydrocarbon, these are the hydrocarbons. These are the hydrocarbons. Why? Because these are making these are forming containing the hydrogen as well as the carbon in the structure. That is why these are the hydrocarbons, and these are fused off your fused aromatic ring. Means the aromatic ring means your benzene. These benzene molecules are fusing and they are forming this polynuclear aromatic hydrocarbon. So these rings share one or more side and contain delocalized electrons. Here means the ring that is your aromatic rings. These are sharing one or more side, means they are fusing, or they are connecting from bonding from one or more side of the aromatic ring, and they are also containing your delocalized electrons. So they are containing the delocalized electrons, means there's also a resonance in the in your aromatic ring. As you know that already know that the aromatic ring is having the delocalization, or you can say that there is a resonance in the benzene ring also. So these are forming from the benzene aromatic ring by fusing one or more sites, and they are also containing the delocalization of your electrons. So another way to consider PAH is molecule made by fusing two or more chains. They are made of fusing two or more benzene rings. Means they are from the benzene ring sides. From the sides, they are fusing. So polynuclear aromatic hydrocarbon molecule contain only carbon and hydrogen atoms. So these aromatic hydrocarbons, they are containing only the carbon and hydrogen atoms. So these are the hydrocarbons. These are the hydrocarbons, or these are the molecules. They are containing your carbon as well as your hydrogen atoms in them. They are not containing the heteroatoms. So these polynuclear hydrocarbons are fusing by the two or more benzene rings, but they so these are molecules that are your polynuclear hydrocarbons. These are molecules, or these are the hydrocarbons that are fusion by two or more benzene rings, and these polynuclear aromatic hydrocarbons, these are containing only carbon and hydrogen atoms. So these polynuclear aromatic hydrocarbons, like in benzene, you know that there is only a presence of your carbon and hydrogen atoms. So in same way, this polynuclear aromatic hydrocarbons, these are also containing the carbon as well as your hydrogen atom. No other atoms are participating in this aromatic ring, or you can say these are not involved in the ring. As you know that heteroatoms, in the heteroatoms there are heterocyclic compounds. There are the heteroatoms that are present in the ring. So the in this case, in this polynuclear hydrocarbon case, there are not presence of any heteroatoms in the ring. That is why they are only made up of, or you can say that they are containing only carbon and hydrogen atoms. So these are the polynuclear hydrocarbons. So these polynuclear aromatic hydrocarbons are lipophilic non-polar molecules. So these polynuclear aromatic hydrocarbons, they are lipophilic non-polar molecules. Means they are lipophilic. Philic means lipid, lipid philic, lipid loving, or lipid liking. So these are uh, the hydrocarbons that are lipophilic and non-polar molecules. These are they are not showing any polarity. They are the non-polar molecules, like your benzene, like your ethers. So these are the non-polar molecules. These polynuclear aromatic hydrocarbons, and they tend to persist in the environment because PAH are not very soluble in water. So they are present in the environment. They are persisting. They have the tendency to persisting in the environment because these PAH, very polynuclear aromatic hydrocarbons, are not very soluble in water. So these are not soluble in water. That is why they are persisting in the environment. While two or three rings PAH are somewhat soluble in aqueous solution. So the pH molecules that are containing two or three rings means they are containing two or three rings that are fused from the side by side, or you can say the two ring means naphthalene, or the three ring means phenanthrene. So these are soluble, these are somewhat smaller, soluble in your aqueous solution, and the solubility decreases nearly logarithmically as molecular mass increases. Means if the molecular mass of the compound or the hydrocarbon increases, then their solubility will be decreases. Means there is if they are fusing a more rings in the structure, more and more benzene rings are fusing in the polynuclear hydrocarbon, it means their solubility is decreasing. That is why it is written here that 2 and 3 polynuclear aromatic hydrocarbons are soluble in water or in aqueous solutions. These are soluble in aqueous solution because they have the molecular mass which is less. And in case if the molecular mass is increasing, then their solubility is also decreasing. So 2, 3, 4 rings PAH are sufficiently volatile to exist in the gas phase. So the containing the polynuclear aromatic hydrocarbons which are containing the 2 rings or the 3 rings or the 4 rings in which the rings are fusing. So in that case, are volatile and they are existing in the gas phase. So these polynuclear aromatic hydrocarbons, these are volatile and they are existing as your gas phase, means in a state of gas. So while the larger molecules, means the larger molecules, means whose mass are larger, or they are containing the more ring, they are fusing the more ring, so they are existing as solid. So these larger polynuclear aromatic hydrocarbon molecules are existing as solids, which are fused by the 5, 6, 7 rings or more. So pure solid polynuclear aromatic hydrocarbons will be colorless, white, pale yellow, or pale green. So these polynuclear aromatic hydrocarbons, they are colorless, white, pale yellow, or pale green color. So the polynuclear aromatic hydrocarbons are lipophilic non-polar molecules, and they tend to persisting in the environment because PAH are not very soluble in water. These are not soluble in water, and they are containing your 2 or 3 rings, and these pH are somewhat soluble in your aqueous solution, and the solubility decreases and merely logarithmically as molecular mass increases, and the 2, 3, 4 pH are sufficiently volatile and they exist in the gas phase, while the larger molecule exists as solid. Pure solid pH may be colorless, white, pale yellow, or pale green color. So these polynuclear hydrocarbons, these are your hydrocarbons. They are made up of aromatic fused ring, and this ring shares one or more sides and contain your delocalized electrons. And these are formed, or these are containing, or these are made of the fusing 2 or more benzene rings, and these molecules contain carbon and hydrogen atoms. These are your polynuclear hydrocarbons, and these are the properties of this polynuclear hydrocarbon. And they are existing, these pure polynuclear aromatic hydrocarbons, they are existing as a colorless. Some are colorless, some are white color, some are pale yellow, some are pale green color. So the pure solids means the larger molecules that are existing as a solid, they are showing these states, these colorless, these color states, and and they are not soluble in water, and they are means in the aqueous solution, and they are volatile, and small rings, means which are fused 2 or 3, 4 rings. They are volatile in nature, and they are not soluble in water, and they are lipophilic non-polar molecules, and they are formed by fusing your 2 or 3 more benzene rings, and they are also containing your delocalized electrons as well. Next, your properties of your anthracene. So in this case, you will see that these are the properties of your anthracene, and the anthracene is your colorless solid, and it melts at 218 degrees centigrade and boils at 340 degrees centigrade. So anthracene is your colorless solid, and these are containing, it melts at your 218 degrees centigrade, and it's boiling as 340 degrees centigrade. And anthracene is insoluble in water but dissolved in benzene. So this anthracene is not soluble in water, and they are having the melting point is your 218 degrees centigrade, and its boiling point is your 340 degrees centigrade, and they are dissolving in the organic solvent, that is your benzene. So it is dissolving in a benzene, and it is a colorless liquid, and it is It is present in the state of solid, and it is showing the color that is not colorless. It shows a strong blue fluorescence when exposed to ultraviolet light. Means when heat is applied or when light is applied, then they are showing a blue fluorescence. Means they are showing the light that is your blue, strong blue color. So this fluorescent property of anthracene is used in criminal detection work, since a small amount of finely powdered anthracene on clothing, skin, money, etc. is not detected under ordinary light but easily noticed when exposed to ultraviolet light. So this fluorescent property that is shown by this anthracene, a strong blue fluorescence. So this property of this strong blue fluorescence is a property of this anthracene that is used in the criminal detection work. Means in the criminal detection, if we have to find out the criminal, then this anthracene is very useful, and small amount, means it's a very small amount of this anthracene is small amount of finely powdered anthracene if we apply it on the clothing, skin, money, etc. But in case of the ordinary light, it is not detectable. But if we notice it under the ultraviolet light, then it is it shows a blue fluorescence. So here, this anthracene is very useful in criminal detection work, and its small amount, finely powdered anthracene on clothing, skin, money, etc. is not detected under ordinary light, but when it is exposed under this ultraviolet light, then it shows a blue fluorescence. So the criminal anthracene undergoes addition electrophilic substitution reaction. So this chemically anthracene, it is undergoing your addition electrophilic substitution reaction. So anthracene is this chemically anthracene is showing the addition reaction as well as your electrophilic substitution reactions. Addition reaction means that a molecule is added, and in the electrophilic substitution reaction means the electrophile will substitute the another molecule or the atom from that molecule, from that compound. So here it anthracene is showing both addition as well as the electrophilic substitution reaction, and these reaction preferentially occurs at the C9 and C10 position. So on the C9 and C10 position, this anthracene is showing your addition as well as your electrophilic substitution reaction. This can be understood if we examine the intermediate carbonium ion obtained from attack at C1, C2, and C9. All of the positions are equivalent to either 1 or 2 or 9 by symmetry, and E plus, that is electrophile, in the following equation represent an electrophile. So in this case, in the properties of anthracene is that physically this anthracene is your physical property of this anthracene is that anthracene is a colorless solid, and it is melting at 218 degrees centigrade, and it is boiling at 340 degrees centigrade. And this anthracene is insoluble in water, and it is dissolving in benzene. So in case of its solubility, it is also showing insolubility in the aqueous solution, but in case of your organic solvent, it is showing its solubility, and it is also showing it is also showing this property that when it is exposed under the ultraviolet light, that it is showing the strong blue fluorescence, and when it is this fluorescence property of your anthracene is used in criminal detection work. So it is used in the work of the criminal detection, and when a small amount of this anthracene is exposed under the ordinary light, then it does not show any fluorescence. But if it is exposed to the ultraviolet light, then it is easily noticeable, and it is when a small amount of this anthracene, finely powdered anthracene, is present on clothing, skin, or money, then it can be easily noticed under the ultraviolet light. Now the chemical property. Chemically, anthracene undergo addition and electrophilic substitution reaction. So it is showing you addition as well as your electrophilic substitution reaction. And these reactions are showing or are occurring at the C9 and C10 position. So here in the structure you can see the ninth and the 10th position of this anthracene, and uh, and this can be understood if we examine the intermediate carbonium ion. So the intermediate carbonium ion that is formed by the attack of the electrophile on the position that C1, C2, and C9, that all of the positions are equivalent to either, means the all of the positions on this anthracenes are equivalent to this first and the second position. So and by 9, by symmetrically, means that we are if we are seeing the structure of this or the positions symmetrically, then these other positions are equivalent to this 1 and 2 position and the 9. So anthracene is in this anthracene, the E plus is your electrophile. It is representing by the electrophile. So you can see here the attack on the C1 carbon. So here this is your C1 attack. This is your C1 carbon. This is the carbon that is present on the C1 position. So it is showing the attack of this electrophile on the C1 carbon, and this C1 on the C1, when this is the structure of anthracene, this is the first position, this is the second position, this is the ninth, the third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So in this, you can see on the first position, you can see there is a attack of this electrophile. So here you can see the formation of this carbonium ion. See here the formation of carbonium ion. Addition, it is showing the addition reaction. So this intermediate obtained from the attack at C1, C2, and C9, all other positions are equivalent to either 1 or 2 or your 9 by symmetrically. So this is the chemical. Next, if the attack is on the next position, so here you can see that if the attack is on the C2 carbon, means on the carbon 2, here this is the C2 carbon, and if this electrophile is attacking on the C2 carbon, then you will see the same here on that attack on the C1, and if it is attacking on your C9, then you can see here it will show this type of structure. So here, attack at C9 yields a carbonium ion intermediate in which 2 benzene rings are attained. You can see here that in this case, in the C9, these are the 2 benzene rings. These are the 2 benzene rings. Whereas on the C1 and C2 is an intermediate in which naphthalene system is attained. Means here you can see in the C2, C1 attack also, this is your naphthalene ring. This is retained here. Okay, and in the C2 also you can see when this electrophile is attacking on the C2 position, then this naphthalene ring is also retained. But in case of the C9, when the attack is on the C9, then you can see that 2 benzene rings are retained here. So the former intermediate is more stable, and its formation favored because the resonance energy of 2 benzene rings exceeds that of naphthalene. So here this former means this is more stable, and it is also favored because the resonance energy, means the resonance energy in this two benzene ring exceeds that of naphthalene as compared to this naphthalene. So you can see in this 2 benzene ring, the resonance energy is your 72 kilocalorie. But in case of this naphthalene, it is your 61 kilocalorie. So this benzene ring, this attack at C19 is more favored and is more stable. That means the intermediate that is formed, that is more stable, and its formation is favored because there is a because the resonance energy of two benzene ring, that is your 72 kilocalorie, exceeds that of naphthalene. So you can see that attack on the C9 yields a carbonium intermediate. This is your intermediate, and in this, the two benzene rings, the two benzene, as you can see, there is a two benzene rings, and these benzene rings are retained. And as well as in case of C1 and C2, this is an intermediate in which a naphthalene system is attained. So in the both the C1 and the C2, you can see the naphthalene system is attained, means two rings are present. And in this case, you can see the four benzene ring. As you can see, these are the two benzene rings that are retained. So the former intermediate is more stable, and here the formation favored because the resonance energy of the two benzene rings are is your 72 kilocalorie, which is more higher than the naphthalene, which is having the 61 kilocalorie. Next is these are the reactions of this anthracene that are showing the electrophilic substitution reaction. So this is the structure of your anthracene, and when there is a electrophilic substitution reaction of this halogens, means here if the halogenation is occurring, then there is a substitution here. The substitution is happening. So you can see that that the ninth position is more fit. So in case of halogenation, you can see there is an attack on the ninth position. So here you can see that this halogen, when this anthracene is undergoing the halogenation, then the electrophile, that is your Cl or your X, that will attack on the ninth position. So there is a removal of the hydrogen, or you can say there is a removal of the proton from the ninth position. After that, there will be a substitution on this halogenation. Means when this will attack to this ninth position, this halogen will attack to this ninth position. So there is a the presence of this hydrogen present on this carbon, then it will be substituted and will remove out from here. So it becomes your 9 halo anthracene. Means on ninth position there is a presence of a halogen. That is why its name is 9 halo anthracene. Now second is your sulfonation. Means if the anthracene is undergoing sulfonation, and there will be a reaction between the anthracene and H2SO4, that is your sulfuric acid. So when this anthracene is undergoing reaction with this H2SO4 or your sulfuric acid, then there is a formation of these two products are formed. That is your anthracene 1 sulfonic acid and anthracene 2 sulfonic acid. So here two products are formed. One is your 1 sulfonic acid and second one is 2 sulfonic acid. So you can see here on the first position also there is a substitution of this sulfuric acid on the first position, and there is a removal of the proton and the H positive from this position. Second case, in the second case also, there is an attack on the carbon 2, and on the carbon 2, there is a formation of this sulfonic acid, and here the removal of your hydrogen is occurring from this position. So this is the electrophilic substitution reaction. So in this, first is your halogenation. So in your halogenation, you can see the halogen is attacking on the ninth position, and from here the removal of the removal of hydrogen occurs, means the proton is removed out from here, and there is a placement of this halogen on the ninth position. So this is your 9 halo anthracene. Secondly, it is your sulfonation. So on the sulfonation, when the sulfonation is occurring on the anthracene, then this is your H2SO4, and in your H2SO4 there is an attack of the sulfuric acid on the anthracene, and there is a formation of this SO3H. Means here anthracene 1 sulfonic acid is formed, and two products are formed, that is your anthracene 1 sulfonic acid, and secondly is your anthracene 2 sulfonic acid. So on the first sulfonic acid, means the attack of the sulfuric acid is on the first position, and in the 2 sulfonic acid there is an attack of this sulfonic acid on the second position. So this is the electrophilic substitution reaction. Next, in the anthracene, when this electrophilic substitution is occurring by the acetylene, and this is occurring in the non-polar solvent. So here in this case we are taking a non-polar solvent, and there is a presence when anthracene is undergoing the acetylation, then there is a acetyl is attacked on the ninth position. So this acetyl is attacking on the ninth position, and there is a formation of this 9-acetyl anthracene. And next is your anthracene. When it is undergoing a nitration, then there is a attack of the nitric acid in the presence of your H2SO4, and this nitric acid, this nitro will attack to the ninth position of this anthracene. So here you can see this anthracene. In the electrophilic substitution reaction, the four reactions are involved. First is your halogenation. In the halogenation, the halogen is attacking on the ninth position of this anthracene ring, and secondly, it was your sulfonation, and in the sulfonation, the sulfuric acid, in the presence of sulfuric acid, the reaction is undergoing, and when this is reacting with this anthracene is reacting with this sulfonic acid, then there is a formation of a this sulfonic acid is formed here. So in this sulfonic acid, you can see the two products are formed on the first anthracene 1 sulfonic acid, and the anthracene 2 sulfonic acid is formed. And the third is your acetylation. So in the acetylation, you can see that it is occurring in the non-polar solvent, and in the non-polar solvent, you can see the acetyl group is attacking on the ninth position. It is attacking on the ninth position of this anthracene, and there is a formation of this 9-acetyl anthracene, and this whole reaction is occurring in the presence of your non-polar solvent. Secondly is your this nitration. So in this nitration, you will see that this anthracene is reacted by this nitric acid in the presence of your H2SO4, and this whole reaction is known as nitration. And in this, the nitro group is attached to the or attacked to the ninth position, and from this position, the proton is removed from here. And then when the proton is removed from here, there is a formation of this 9-nitro anthracene is formed here. So this is the fourth LiPo reaction that are involving under the electrophilic substitution reaction. Now again, the anthracene in the presence of this, if it is going the acetylation in the presence of your polar solvent, if it is undergoing in the presence of the polar solvent, in the last reaction, we have seen that the anthracene is undergoing reaction under the non-polar solvent, and if this anthracene is going under reaction acetylation reaction in the polar solvent, then there is an attack of this acetyl group on this first position, and the non-polar solvent, it is attacking on the ninth position, and in the polar solvent, it is attacking on the first position. So there is a formation of this 1-acetyl anthracene is formed. Next is your anthracene. In this, the anthracene is attacking on the anthracene is showing on this H2SO4 in showing the reaction with this H2SO4, and they in the presence of your high temperature. In the high temperature, in the presence of the high temperature, as this anthracene is reacting with this H2SO4, and there is a formation of this anthracene 2,7-disulfonic acid. But in that case, and when anthracene is reacting with this H2SO4 normally, then there are two products are formed, that is your anthracene 1 sulfonic acid and the anthracene 2 sulfonic acid. So here you can see this anthracene is showing H2SO4, showing the reaction with the H2SO4 in the high temperature. There is a formation of this anthracene 2,7-disulfonic acid, and at low temperature, it is showing anthracene 1,8-disulfonic acid. So at the high temperature, the anthracene is showing anthracene 2,7-disulfonic acid, and at the low temperature, it is forming anthracene 1,8-disulfonic acid is formed here. Next is a diol-alder reaction. So in case of this, anthracene undergoing diol-alder reaction at the 9th and the 10th position and form endo-anthracene malic anhydride. So in this case, in the diol-alder reaction, This anthracene is undergoing diel-Elder reaction at ninth and 10th position in forming a endo-anthracene malic anhydride. So there is a product formed, this adduct product is formed with this malic anhydride reaction. When anthracene is undergoing reaction with this malic anhydride, there is a formation of this diel-Elder product. So here you can see this on the from on the ninth and the 10th position, this malic acid is attacking. So here this ninth and the 10th position, this one from this bond and the another from this bond, it is forming a bond, and there's a formation of this product is formed here, and you can see there's a from this the double bond is removed from here, there is a formation of this adduct is formed here. Endo-anthracene malic anhydride is. Next is your oxidation. So anthracene, when undergoing your oxidation with your sodium dichromate and sulfuric acid, there is a formation of this 9,10 anthraquinone. So in the presence of this oxidant, that is your sodium dichromate, and in the presence of this oxidant, that is the sodium dichromate, and in the presence of the sulfuric acid, there is a formation of this 9,10 anthraquinone, and of this anthraquinone. From this anthracene, this anthraquinone is formed by the oxidant, that is your sodium dichromate. So there is the oxidation is occurring here. So from the oxidation, this anthracene undergoes oxidation in the presence of the sodium dichromate and sulfuric acid. There is a formation of this 9,10 anthraquinone is formed here. Next is your reduction. So reduction in the anthracene, on reduction, it is undergoing the reduction with the sodium and ethyl alcohol, and there is a formation of the 9,10 dihydroanthracene. So here there is an addition of the hydrogen on the 9th and the 10th position. So here the product that is formed is your dihydroanthracene. As you can see, there is a one H hydrogen is already there, and there is a presence of on reduction, there is the addition of these hydrogens are occurring on the 9th and the 10th position in the presence of your sodium as well as in the ethyl alcohol. So anthracene on reduction with sodium and ethyl alcohol, they are producing this 9,10 dihydroanthracene, and there is a formation of this 9,10 dihydroanthracene is formed here. So this is your reduction reaction, and in the presence of the oxidation, oxidation is happening in the presence of sodium dichromate and as well as in the H2SO4, and there is a formation of 9,10 anthraquinone is formed, and here 9,10 dihydroanthracene is formed here. After reducing, this anthracene is reducing, there is a formation of this dihydroanthracene is formed here in the presence of this ethyl alcohol as well as your sodium. Dimerization. So here the dimerization of this anthracene is occurring in UV light, and there is a production of this dianthracene. Means in the presence of this UV light, the two molecules of this anthracene are reacting, and there is a formation of this dimerization. Means they are forming a di molecule. So here you can see on the 9th and the 10th position. Sorry. On the 9th and the 10th position, you can see there is addition of this your methyl groups as well as, and they are adding on the 9th and the 10th position. You can see this is the 9th and this is the 10th. This is the 9th and this is the 10th. So there is addition of this methyl group on the 9th and the 10th position, and on the 9th and the 10th position, this dimeric product is also formed here. This is also formed here. And there is a formation of this dianthracene, and this reaction is known as your dimerization. And in your dimerization, this is occurring in the presence of your UV light and and there is a formation of this product that is your dianthracene. So the first is your electrophilic reaction. In your electrophilic reaction, in your First is your this electrophilic reaction. In the electrophilic reaction, we have already done what we have shown the anthracene is undergoing halogenation. So there is a on the ninth position there is a formation of this 9 halo anthracene. Secondly, it is undergoing with sulfonation in the presence of your H2SO4. There is a formation of two products, that is the anthracene 9 sulfonic acid, or the and the anthracene 10 sulfonic acid. Third, it is your acetylation. So acetylation of anthracene is occurring in the presence of non-polar solvent, and there is a formation of this 9-acetyl anthracene. Next, it was your nitration. So nitration is occurring on the ninth position. So in the ninth position, there is a formation of 9-nitro-anthracene is formed there. Next is your anthracene. When anthracene is undergoing with the acetylation in the presence of your polar solvent, and that reaction is undergoing on the first position. So the anthracene 1 acetyl anthracene is formed there. And secondly, it was your when anthracene is reacting with the sulfonic acid in the presence of sulfuric acid at high and the low temperature. So on that, the anthracene 1,7 disulfonic acid is formed, or 1,8 disulfonic acid is formed, means sulfonic acid is formed. Okay, after that there is a oxidation. So oxidation in the presence of sodium dichromate, this is forming a 9,10 anthraquinone, and in the reduction happening in the presence of the sodium and C2H5OH, that is the ethyl alcohol, and there is a formation of this 9,10 anthron is formed. Next, it is your this dianthron is formed. Next is your this dihydroanthracene is formed. Next is your dial elder reaction. So in that, there is a formation of dianthracene, or a dial elder product is formed. Next, in the dimerization, there is a formation of dianthracene is formed. Like dianthracene is formed, and in the dial elder reaction, there is a product that is formed is your endoanthracene malic anhydride, because this reaction is undergoing with the anthracene with the malic anhydride. So there is a formation of this endoanthracene malic anhydride. Next, these are the derivatives of the anthracene. These are the four derivatives of this anthracene, that is your anthraquinone, anthrone, oxanthrone, anthrone. So the medical uses of this anthracene is that anthracene glycosides are oxygenated derivatives of pharmacological importance that are used as laxative or cathartic and anti-neoplastic agent, polycystic kidney. This is your amodin. Next is your anti-inflammatory, antibacterial, antifungal, and proliferative activity. And these derivatives of this anthracene is showing, and it is also acting as a natural dyes, and this is also acting as a hepatoprotective, nephroprotective antioxidant. Now next is your diphenyl methane. So diphenyl methane is an organic compound that is having the formula this, and the compound consists of methane, wherein two hydrogen atoms are replaced by your two phenyl groups. And in this, the common skeleton is in the diphenyl methyl group is also known as your bench hydride, and it is prepared by your Friedel-Crafts alkylation of benzyl chloride with benzene in the presence of Lewis acids such as your aluminum chloride. So here you can see this is your diphenyl methane structure, and it is prepared with this benzene as well as your benzyl chloride. There is a formation of this dimethyl methane. So this is the structure, and from this compound in the presence of hydrogen iodide, and there is a formation of this dimethyl methane. So these are the derivatives of your diphenyl methane, that is your bench hydrol or benzophenol. So the medicinal uses of this, that it is used in the synthesis of limogens for aggregation, induced emission, and it is also used in the preparation of polymerization. It is widely used in the synthesis of luminogens for aggregation, induced emissions, and it is also used in the preparation of polymerization initiator, diphenyl methane, potassium It is also a precursor in the synthesis of a dendrimeric polycyclic aromatic hydrocarbon hexix and benzene, phenylbenzene. The main application of this trimethyl includes the remotion for aggregation and emission and is also used in the preparation of a polymerization initiators and diphenylmethyl potassium. It is also one of the precursor. It is used in the synthesis of a dendritic polycyclic aromatic hydrocarbon hexix and the benzene. This hexix benzene. Next, the synthesis. This is the synthesis of this dimethyl methane and the chemical properties. This is occurring as a colorless to pale yellow, low melting solid, and it is occurs in the has apparently not been reported to occur in nature. And the metabolism it is hydrolysis in the rabbit, and some it excreted as 4 hydroxy diphenylmethane, which is largely 80-90% in the free state. Neither the hydrocarbon nor its metabolite is osteogenic, and this reaction also occurs in the dog. Purification method: if we sublimize it under a vacuum or distill it at the 172 to 750, then it is recrystallized with cold ethyl alcohol. It has been purified by fractional distillation from the melt. Next is your trimethyl methane. So this is a trimethyl methane structure and is a chromogen of a large number of dyes, and the common chromophore is the p-quinone structure, and the oxochromes are OH, NH2 and NR2. This is a brilliant intense color. It gives a brilliant intense color but fade quickly in light. Therefore, they are no much longer used on textiles and in the large quantity for coloring paper and typewriter ribbons, where plasticenses to light is not so important. Next, this is a hydrocarbon with the formula C6H5O3CH. This is a colorless solid which is soluble in non-polar organic solvent and not in water. And this diphenylmethane is the basic skeleton of many synthetic dyes, and it called the triaryl dyes, and many of them are pH indicator, and some are also displacing this fluorescence. And this is a trityl group in organic chemistry is a diphenyl methyl group. And for example, is the dimethylphenyl chloride or the diphenyl methyl radicals. Next, reaction of the CH bond. So it is showing this type of reactions, and it is having a non-nucleophilic base that has been eclipsed by the polymerization of butyl lithium and related strong bases, and it is a relatively weak. This bond is relatively weak, and with the bond dissociation energy of 81 kilocalorie per mole, and this is having a pK that is your 33.3, and it is more acidic than most of the other hydrocarbons because the charge is delocalized over the 3-phenyl ring. And the steric effect, however, prevent all 3-phenyl ring from achieving copolarity simultaneously, and this is even more acidic because there is an anion charge that is spread over the 2-phenyl rings at the same time, and this tritial anion is red, and this is also used in the indicator in your acid-base titration. So this is the preparation of your trimethyl methane, and these are the derivative of your trimethyl methane, that is your gentian violet and your orange, crystal violet, malachite green, and it is also used in the detergent, fertilizers, and textile dyes. And it is also used in copying paper, in hectograph, and printing inks. So this is the questions. What is the diffractive resonance contributor of naphthalene? That is a C. More probable main product of the following reaction is a B, which is not aromatic, that is your B. Which of the following is not an allyl anion anaglobule, that is your A. Which is impossible as a resonance contributor of anthracene, that is your B. And which is the resonance contributor of the intermediate naphthalenium ion in an electrophilic substitution reaction of naphthalene, that is your A. And naphthalene give dibromo substitution product with bromine in ethanoic acid, and which most likely structure of this compound is your D, and which is most basic, that is your C. And benzene has a stronger van der Waals forces than methylbenzene, that is your A, and it is not represented as arene compound, that is the picric chloride. And which among is the simplest example of polycyclic arene is your naphthalene, and it is polar, bearings are polar or not, that is a false. These are the references from where you can study this topic. Thank you so much for today's lecture.